Hi everyone, this is the Aspen Plus tutorial for part 1. And this tutorial will be talking about heat exchangers and how to model heat exchangers in Aspen, how to troubleshoot some issues with heat exchangers and other issues. Okay, all of you should have taken heat transfer. So you can read this introduction to try and remember different types of heat exchangers, co-current heat exchangers, counter-current heat exchangers, other issues, etc. And two things you always need to remember is when you have a co-current flow arrangement, basically both your hot streams and cold streams are flowing in the same direction. This is what the temperature profiles would look like. And the distance between the hot and the cold should always be equal to, or the minimum distance between the hot and the cold streams should be equal to delta T minimum, right? This way you will always have a driving force for the heat to move from the hot stream to the cold stream. And because, if you don't have a driving force, you won't be able to achieve heat transfer, right? If their two temperatures are too close, the heat transfer will not be fast enough to happen within your unit. And this is what the temperature profiles look like for a counter current flow arrangement. And as you can see here, the hot stream decreases, cold stream increases. However, the minimum distance between these two lines should be equal to delta T minimum, okay? So this is something very important to remember when doing heat exchangers, when working on your projects or any other thing, Okay, so in this tutorial, this is the case study. I have pure M-butanol produced at a flow rate of 1,000 kilograms per hour and 2 bars from an upstream distillation process, and it needs to be cooled down from 117.7 degrees Celsius to 40 degrees Celsius before it can be stored in a tank. Okay, so I have 1,000 kilograms per hour of N-butanol, pressure 2 bars, and I need to cool it from 117.7 to 40 degrees Celsius. Cooling water at 25 Celsius and 2 bars is available to provide the cooling. And so we need to create a new Aspen simulation, metric units, and we're going to use the Wilson model to represent our system. So let's do this first step here. So I'm going to go to Aspen. I already opened Aspen. I have a new simulation running. And I'm in the properties tab. So if you find yourself in another tab, just go in the bottom left here, navigate to the properties tab. First thing I'm going to do is on the tree on the left-hand side, I'm going to click on the arrow next to setup, click on specifications, and I'm going to define this, set my units to metric. After this, I'm going to go under the folder components. The first element here is specifications. If you have this folder closed, you can just open it by clicking on the small arrow to expand the tree. Click on specifications, and we said we need 2 chemicals. First one is N-butanol. So let me find it. So I'm going to click on find. Okay, we want butanol. I think I can just write N-butanol, and Aspen will find it. Here we go, N-butanol here. C4H10O1, right? It's fine. And I'm going to add selected compounds, and it's going to show up, and then I'm going to close out. And then for water, I'll just write water, and Aspen Plus should be able to recognize it. One thing when adding these chemicals, make sure that it shows up in these columns as well, right? If you misspell water for some reason, or yes, the most common error is misspelling. So if you misspell water and it doesn't show up here, Aspen will not recognize the chemicals. Okay, so we have the 2 chemicals we're interested in here, and after specifying them, I still have a red dot next to methods, and this is normal. Your tutorial actually mentions this, so if you go back to the tutorial, it says here, you will probably have the red required input incomplete notification showing. Okay, sorry, this is because the binary interaction parameters for M-butanol water have not been loaded in the Wilson model. click on the methods, parameters, binary interaction, Wilson 1, form to load it. So this is what we're going to do. We're just going to navigate methods, parameters, binary interaction, Wilson 1, to load these binary interaction parameters and get rid of this, this error. So I'm going back to my simulation file. We said methods. I'm just expanding the file here. Specifications. Give it a second. Oh, we didn't actually specify the equation of state, sorry. So yeah, I guess that's the next step. So for now, let's just specify the equation of state. We said we want to use the Wilson model. So let's just select the Wilson. And yeah, so now the red arrow appears under parameters. So what we're going to do is, as written in the tutorial, we're going to navigate methods, parameters, binary interaction, Wilson 1. So methods, parameters, binary interaction parameters, and it will automatically retrieve all these parameters, and you're going to get the blue check, and the red circle is going to go away, so that's fine. So this is common when using you know, polar and non-polar chemicals or organic, inorganic chemicals. Aspen does not automatically retrieve these binary interaction parameters, and you just have to navigate to the binary interaction folder, and it will navigate, and it will retrieve them basically. Okay, so now everything is set up, you know. We defined our chemicals under specifications. We defined our methods. We were going to use the Wilson method. So let's go back to the tutorial and see what does it want from us. Okay, here we go. So in this video, I'm just doing part 1. We're going to do part 2 next week. And one thing to note about Aspen, there you have 2 types of models. You have the heater model, and then you have a heat exchanger model. The heater model here was basically a half heat exchanger. It models only one of the 2 fluids in the heat exchange process, right? So in this heater model, I only have one stream from temperature 1 to temperature 2. It's not a full heat exchanger. It's just a heater or cooler that's going to achieve this manipulation, heating manipulation or cooling manipulation, and it will give you a heat duty requirement. So it's not a true heat exchanger in the sense I have 2 chemicals, I have 2 fluids flowing in the same direction or opposite direction, and their temperatures are changing. So in part 1, we're looking at the heater model, and in this heater model, you need to give it 2 pieces of information for it to solve: the outlet temperature, you know, the outlet pressure, vapor fraction, or heat duty. So if you remember from the previous tutorial, we actually added a heat stream, and it removed one of these degrees of freedom, and we just had to specify one of them. But basically, this heater model only needs 2 pieces of information to function and to solve. Okay, so let's see what this tutorial wants. In the model library at the bottom of your screen, click the exchanger tab, and then we're going to select the heater model, and we will use it to figure out how much cooling is required by the butanol stream. Okay, that's fine. So let's do this. And then, you know, here you have all your inputs and outputs for these for this unit. So I'm going to drop a heater model. I'm going to connect, of course, the mass stream, and then I'm going to specify the inlet to be butanol, 117 Celsius, 2 bars, 1,000 kilograms per hour. And then specifications of this heater will be, you know, the outlet temperature has to be 40 Celsius, and there's no pressure drop, or the pressure will be 0 bars. Okay, so let me share the Aspen window, and let's do this. So I'm done with properties. So on the bottom left here, I'm going to navigate to simulation. Give it a second. And if for some reason you're not seeing the model palette, let me close that. If you're not seeing the model palette, you're not seeing your flow sheet, you're not seeing anything, just go here to the top to view and just activate it, so you can activate the model palette. You know, if it disappears, just click, it's gonna show up again. If your flow sheet is not showing, click on flow sheet, it will show up again. So just Don't panic. These things are normal in terms of the workflow of Aspen. You might close it out by mistake or anything. That's fine. So we have our main flow sheet. I'm going to navigate to exchangers here, and I'm going to drop the heater model, and then I'm going to add an inlet stream and add an outlet stream. And again, always remember with Aspen, you always have the sticky cursor type of thing. So after dropping a stream, after connecting a stream, make sure to click on escape so that you get your normal mouse back. Otherwise, it will just get annoying. It will keep on dropping elements and stuff. So here, what we expect is I have butanol going in at 117, coming out at 40 Celsius. So this is actually a cooler, right? So I'm gonna rename this. I'm gonna rename it cooler, right? Or cooler is fine. And then I'm gonna rename these streams butanol in and butanol out, right? Butanol. Okay. Say butanol in, BOH, okay, and BOH out. I think this is what the tutorial is using, so we'll use the same naming convention. Okay, so now I have, I just have my figure here, or I have my elements here. So now let's define the inlet. So I need to define the inlet and I need to define the heat exchanger. In order to do this, I can always navigate from the tree. So I can navigate to streams, BOH in, input, and always you just give it the input. Don't specify the output. If you specify the output as well, you're solving the problem. So I mean, what's the point of using Aspen? So always just specify the input. Okay, and here I'm just following the figure in the tutorial, and I have temperature, pressure, 117.7, 2 bars, and 1,000 kilograms per hour. So here in Celsius, I have 117.7. Pressure here is 2 bars. My flow rate is a mass flow rate. Again, be careful with this. This is a common area of error where you don't specify whether it's mass or moles or the flow basis is. And then this is a second area of error where you don't specify whether you're using molar flow, molar fraction, mass fraction, mole fraction, whatever. Here it's only butanol, so I just need to select either mass fraction or mole fraction and set it to 1. And once I do this, you can see that I get the blue check here, and so we don't need to specify any more information. Second thing we need to specify is under blocks, cooler. So you can navigate to it from the tree, or you can double click on it on the main flow sheet. And here I'm going to go to input for the cooler. And I'm just going to follow the figure in the tutorial. So outlet temperature will be 40 and the pressure drop will be 0 bars, right? So again, be careful with the units. I want this to be 40 Celsius, right? And my pressure drop will be 0. I mean, you can specify any unit you want because it's 0 bars. And that's it. So let's run this. Let's run this simulation and see what Aspen is going to give us. Let me save it up first. I'm going to call it tutorial 4. Save, and then to run it, you just click on the the play button, or you can click on next. If you click on next, this will tell you everything's complete. Run it. Okay, run it. Give it a second, and we will get the results now. Okay, while we're waiting for the results, let me just navigate back to the tutorial and have a look here. So we did all of this, and then you have question 1, how much cooling is required by the process in kilowatts? So I need to basically find the cooling requirement of this heat exchanger. So so this is still running. Let's give it a second. Okay, so I have a warning here. Warning in physical properties, absolute values exceptionally large for data set. This, okay, it doesn't matter. It's just a warning, it's just a calculation warning. You might not get this error. I think it depends on your processor. So it's fine. So there's nothing here. Everything is blue checked, so everything's fine. So in order to find the heating requirements for the cooler, for this heat exchanger, I navigate under blocks. I look under results here. And you can see I have your heat duty, your net duty. And for question 1, we're asking how much cooling is required by the process in kilowatts. So we really need the heat duty, which is, what's the requirement, and in kilowatts. Again, these should be the same. So your duty for this heat exchanger or for this cooler is minus 69.47 kilowatts. Okay, so this is the answer for question number 1. And again, all we did is I dropped this heater model. I connected the input, the output, provided the information, ran it, and then I navigated to the results from the tree on the left-hand side. Okay, let's go back to the tutorial. Let's have a look here. So we're done with this. Now that we know how much cooling is required, we can figure out how much water we should use to provide it and what the outlet conditions of the water stream would be. Given some text here as well. And then you're being asked, add another heater model to your simulation, as well as input and output streams. We know the temperature and pressure of the inlet water stream, but we don't know the flow rate. So let's choose something random for now, 600 kilograms per hour. Okay, so I'm gonna add a second heat exchanger, and it will have a flow rate of 600 kilograms per hour. It will have no pressure drop, right? So I have 600 kilograms per hour, no pressure drop. And the second degree of freedom will be the heat duty, which we know from the results of the cool heat model. Okay, so what we're gonna do next is we're gonna add a second heater. This one will be for the water. I'm gonna introduce water using the specs given in the prompt at the very top here. 25 degrees Celsius and 2 bars. This is the cooling water we're using. So I'm going to introduce water at 25 degrees Celsius and 2 bars at a flow rate of 600 kilograms per hour. And then for the heater model, my 2 pieces of information I'm going to give it. The first one will be no pressure drop. And then the second one will be the heat duty, which I'm going to transfer from the cooler or from the other heat, from the other heater we simulated. Okay, so we're basically going to do this now, and then we're going to run it. And we need to find what's the outlet temperature of the water stream in degrees Celsius. So I need to find the outlet temperature in the outlet stream from the hot heater here. Okay, so let's navigate to our tutorial. Let me close out of these tabs. And let's go to the main flow sheet here. So now I need to add a heater. And I'm going to connect 2 streams, an input and an output. If you want this to match the figure in the tutorial, you want them to go in opposite directions, you can always right click on this image, click on rotate icon, and we want to flip it horizontally, right? And then you just move the arrows so that it matches. I'm gonna move this arrow here, and this guy is still see if we can how do you make these arrows turn around? Doesn't matter, it's just a cosmetic thing. I mean, if you really want them to turn around, you can just delete them and add them again after rotating the heater. You can always do this. Okay. Doesn't seem to be working for this guy, but it's fine. We just keep moving it around. It should work eventually. Anyways, so I have the so this will be the water. So I'm gonna rename this heater here. I'm gonna rename it similar to the tutorial. I think it's called hot. And then I'm gonna rename this input stream. I'll call it H2O in, and I'll rename this output stream. Call it H2O out. Good. Here we go. Yeah, you just need to move it around. Okay, good. Now it makes sense. Okay, so let's start by specifying the inputs for this stream. Again, I can navigate to it from the left-hand side. You can just double-click here. So I'm going to double-click here, and we said the water is coming in at 25 Celsius. So 25, I'm going to change the unit to Celsius. And 2, I'm changing this unit to bar. And we said the mass flow rate was 600 kilograms per hour. And I'm going to specify the composition, mass fraction to only be water. So I'm going to change it to mass fraction here and then make this 1. Okay, so this stream is specified. So now I need to specify the 2 degrees of freedom required for the heater model. And we said the first one will be pressure drop is 0, and the second one will be the heat being transferred from the cool stream. So while we're on this page, let's draw the heat one. So my mouse now is at the bottom left here on material. I'm gonna click on the small arrow next to material. I'm gonna select the heat, not the work. Heat exchangers don't do work, right? Only compressors and pumps do work. Heat exchangers, they transfer heat. So I'm gonna click on heat. And I'm gonna just connect it from the output of the cooler to the input of the heater or the hot, whatever. Just make sure they're actually connected properly, okay? And this will be the second degree of freedom. And the first degree of freedom, I'm just going to specify it now. And basically the pressure drop will be 0 in this case. So let me go to bar. And 0 here. And as you can see, everything is blue. I don't have any red. The yellow means this yellow diamond basically means that the results have to be updated because we changed the flow sheet, right? And the yellow diamonds will only appear next to the elements we already ran during the last iteration of the simulation, right? Okay, so everything here is set. So I have everything set. So I'm going to run it. And question 2 is asking about the temperature of this stream. So let's run the simulation. So you can always click on these guys at the top. It's fine. Let's run it. Okay, so it's ran. Everything is good. So I need the results of this H2O out. And again, I can navigate to this stream by either double clicking on it. I can navigate to it here from the left-hand side in the tree, just find the stream name H2O out, click on results, or I can click on all the results here. So let's look at all the streams at once. So results, summary streams. Just have a look at all the temperature. Give it a second, let it load. Okay, so I want the temperature for H2O out. Let me change all these to Celsius because this is what we used. So butanol in 117, butanol out 140, H2O in 25, H2O out 120.162. So the outlet water stream leaves at 120.162. And you see here we have a thermodynamic error because the cooling liquid is leaving at a higher temperature than the inlet of the hot stream, right? So there's a crossover here. We're gonna need this. So anyways, so the answer for question number 2 is 120.162. That's the temperature of the water outlet stream. Let's go back to the tutorial. That's the outlet temperature. It was 120.162. So that's how it is. Okay, so let's continue here. If you have modeled this according to instructions, the outlet temperature of the water stream will be higher than the inlet temperature of the butanol stream. So this is what we have. The outlet of the water was 120.1. The inlet of the butanol was 117.7. This is called the temperature crossover, and it violates the second law of thermodynamics because heat will never spontaneously flow from a cold source to a sink of a higher temperature. So the situation we have at the moment is we have a temperature crossover, which in one heat exchanger, so if in a realistic case or when designing a heat exchanger, it's thermodynamically not possible, right? So what we did in Aspen was just a mathematical representation of this, and because we used two different models, Aspen did not recognize that this is a violation, just solved them independently. However, when designing a heat exchanger, you always have to be careful not to have a temperature crossover, right? So the water, outlet of the water and the inlet of the butanol, they should always maintain a distance equivalent to delta T minimum, or maintain a driving force, temperature driving force equivalent to delta T minimum. If we go up here, so this is really how it should look in a good design, or in a design that works, where this distance should be at least equal to delta T minimum, which we didn't achieve in our case. We had a crossover. So, and here it talks about the approach temperature, delta T minimum, all of this stuff. So you can always read this, but we're gonna make a small modification. So for our design, let's use a delta T minimum of 10 degrees Celsius. And then using this, we're gonna use a design spec. Remember the design spec from last time. And we're gonna use a design spec to determine the amount of flow rate that gives us this approach temperature. So basically I'm gonna use a design spec to determine the flow rate of water required to maintain this delta T minimum to be 10 degrees Celsius. Okay, so I'm going to set up a design spec in Aspen Plus, and I'm going to follow basically these windows here, and we're going to basically find the flow rate of water to ensure that delta T minimum is not violated. So let's do this. Let's go back to the simulation here. And in this case, I'm looking to build a design spec. So let me close out these trees so it's easier to see where I'm navigating. So here, under flow sheeting options, design specs, and I'm gonna set a new design spec, and let's call it B temp in, similar to the tutorial here. Or actually the tutorial calls the design spec DS1, right? So let me delete this. Let's rename it properly. So I'm gonna delete this guy. Let me go here. Delete. Okay. Then I'm gonna call this guy DS1, similar to the tutorial. And so the variable is actually called B temp in. So I'm going to call this B temp in. So it's just the variable name. And here is the variable we just defined. You can always click on new and give it a name. It's the same thing. And we're looking at streams. The type of stream we're looking at here is the stream variable. The stream we're interested in is the butanol going in. We're interested in the variable we're interested in is the temperature. Okay, so what I'm doing, first of all, I'm gonna define three things, or I'm gonna define two things actually. The first one is the temperature of the butanol going in, and the second variable I'm gonna define is the temperature of the water exiting. And I'm gonna use these two variables to set my driving force, which is delta T minimum, okay? So I'm gonna create a new item here. I'm gonna call it W temp out, and this is the temperature of water leaving So it's going to show up, and again, it's a stream variable. The type of variable here is stream variable. Let me find it, stream var. The stream is H2O out in this case. And this is a temperature. Okay. Temperature units K. Let's just match the tutorial and make them both C. Delta C and delta K are the same, but just for consistency's sake, we're just going to make them both C. So here at the top, you can see the summary. So I defined two variables for this design spec. First one is the butanol temperature in. The second one is the water temperature out. And here it's a stream variable. The stream is butanol in. Variable is temperature, units is C. And here it's a stream variable. The stream is water out, H2O out. So it's a, it's a temperature with the units of C. So I have my two variables of interest to get this delta T minimum. So now what's the spec? The spec will be, I want B temp, or here is also a common error to misspell these variables, and you have to spell them the same way you define them. B temp in minus W temp out. So this is my delta T minimum, the driving force actually. I want this to be 10, so my delta T minimum has to be 10. And the tolerance, we're going to define it as 0.01, similar to what the tutorial defined. So here, I define the two temperatures I'm interested in. I set the spec, which is butanol temperature in minus water temperature out, and this has to be equal to a delta T minimum of 10. And I set a tolerance for the calculation equal to 0.01. And so what am I going to vary to meet the spec? We said we're going to vary the flow rate of water. So let's do this. So I want to vary the flow rate of water. So the type of variable I'm looking for is a stream variable. So it's a stream variable. The stream I'm interested in is the water stream going in. So it's going to be H2O in. And the variable will be the mass flow rate, right? Mass flow. And it's in kilogram per hour. And let's vary it from 400 to 1,000. Okay. So what I'm going to do in this design spec, I'm going to change the flow rate of water from 400 kilograms per hour to 1,000 kilograms per hour and find the flow rate which will meet the spec of delta T minimum. And we define the spec as the temperature of the butanol in minus the temperature of the water out. We set it to be equal to 10. Okay, so this is how we define a design spec. Just to try to, it might be, not very familiar at first, but once you practice it a bunch of times, you're gonna get there. Okay, so once we have this, let's run this design spec and have a look at the results. And this result will actually give us the flow rate of water, or the minimum flow rate of water required to maintain this driving force of 10 Celsius in our heat exchanger. So let's run it, and then we'll have a look at the results of the design spec, and this will be the end of tutorial 4 part 1 for this week. Okay, so we ran it. Results available, you see it here at the bottom left. Let's navigate to the results. And again, to navigate to the results of design spec, you just expand the design spec tree, you select the design spec you're interested in, and you go to results. So look here. And as you can see, the results here, the manipulated initial value, final value, B temp in, W temp out. So the flow rate of the water is now 697.607, and this will achieve a delta T minimum of 10. So if my flow rate of water going in is 697, then the temperature of the water leaving will be 107.7, which is 10 degrees below the 117.7 for the butanol going in. Okay, so for question number 3, the answer is 697.607. This is the flow rate you need from this in order to maintain the driving force. Let's go back to the tutorial. What's the flow rate of water in kilograms per hour that ensures delta T minimum is not violated? The number we got was 697.607. Okay, so this is the end of tutorial 4 part 1. Try it. If you're having any issues, just please come to office hours. Don't give up on these Aspen tutorials. Just please work through them. You can submit them. You have a lot of time to submit them. Even if you submit them, if you're falling behind, just please submit them to get some points. and learn Aspen. It's a very important skill. Thank you very much.